So here's the key to Maxwell's displacement current, or what Maxwell recognized that Ampere missed out on, is that if there's a magnetic field here, there's a magnetic field here and here, there's a magnetic field here and here, there's a magnetic field everywhere, right? There's a magnetic field everywhere around this wire. So how could there not be a magnetic field here? Well, you might say, well, why shouldn't there be a magnetic field there? Well, there's no current for me to enclose, right? So if I put an Amperian loop, Ampere's law does not work because I put an Amperian loop in between those capacitor plates. It's enclosing no current, so Ampere's law would tell me, right, because this is I enclosed, Ampere's law would tell me that this side is 0 and that the magnetic field here is 0. Yet there's a magnetic field here and here. So what Maxwell recognized is that the magnetic field should be continuous and that there should be a magnetic field in between these capacitor plates as well. What we do know is in between the capacitor plates is that we know that there's a moving electric field. We know that the electric field between the capacitor plates, because this is an AC power source, it's going from a plus charge here and a minus charge here, and it's switching so that there's a minus charge here and a plus charge there. And the charge, remember what an AC power source does, is it pushes charges and pulls charges from the plates. So it's going to switch the charge distribution on the plates from plus to minus to plus to minus. And that's going to give us an electric field that oscillates, pointing towards one plate, then towards the other plate. Hence, I'm putting an arrow on both sides, right? Sometimes it's going to point that way, sometimes it's going to point that way. So there's a changing electric field in there. But because we know that there's a magnetic field everywhere around the wires, that magnetic field must continue on through these plates. And what Maxwell recognized is that the magnetic field that Ampere was correct, but he just left off this concept that there's some kind of imaginary current between the plates that gives us the magnetic field between the plates as well as anywhere around the wires. Oops, D, not B. I displacement. It's called the displacement current. And what Maxwell was able to show, and this is the part where you just got to take it as given at this point, what Maxwell was able to show is that the displacement current has to do with that changing electric field between the plates. I realized I called this I0, that should be I enclosed, in the Ampere's law, plus mu naught I displacement. So what Maxwell was able to show is the displacement current has to do with the time rate of change of electric fields. And again, so in the brackets, in the square brackets here, that's what Maxwell was able to show, that this concept of displacement current, this imaginary current between the plates, is due to the fact there is no actual current. There is no actual current. It's just this term that he called displacement current, so it looks like Ampere's law. There is no displacement current. There is no current between the plates. It's just that he called it a current to make it look like Ampere's law, so that it's really just either there's a current or there's a changing electric field. And that's what he's showing, is that where there's a changing electric field, it's got the same effect as there being a current. And therefore, changing electric fields must create magnetic fields. Again, where there's a changing electric field, it's got the same effect as if there's a current. And we know that currents create magnetic fields. Changing electric fields also create magnetic fields. Totally made a small error here when I wrote this. I wrote dE dt. That should be d flux dt. Electric flux. That should be electric flux. Okay, sorry, I wasn't able to fix that adequately. I had to, redraw it. The displacement current is epsilon 0 times the time rate of change of electric flux. Not the integral of time rate of change of electric flux. It was the integral of E. It was confused. But anyway, so the displacement current is epsilon 0 time rate of change of electric flux, which is equal to epsilon 0 times the time rate of change of the integral
of E dot dA. Okay, so that's the displacement current. I had left off the dot dA before, right, and just said it was dE dt. Okay, so in summary, Maxwell's equations are now these four equations with Ampere's law modified by Maxwell's displacement current.